Class, so now we're going to discuss geometric sequences. In the last couple of videos, we talked about arithmetic sequences. That's a sequence where every term in the sequence differs by a constant. So let's say 1, 3, 5, 7. In this case, our difference, what we're doing every time, is we're adding 2. For geometric sequence, instead of adding, we're multiplying. So let's say I had 1, 2, 4, 8, 16. You can see that each time I'm multiplying by 2. Okay, so we're going to discuss more about these types of sequences. So a geometric sequence is a sequence in which each term is found by multiplying the first term by a common ratio, r. Okay, and we can find this using the formula a sub n plus 1 over a sub n. So again, just like with arithmetic sequences, I want to check every pair just to make sure it's really geometric. So I have r equals 2 over 1, which is 2. R equals 4 over 2, which is 2. R equals 8 over 4, which is 2. And r is 16 over 8, which is 2, right? We take the ratio of the term, the second term to the first term, third term to the second term, and so on and so forth. So this is an example of a geometric sequence. So let's find the common ratio of these series. So like always, I'm going to take my second term divided by my first term, okay? Right? Because the formula is a sub n plus 1 over a sub n. And let's say n equals 1, then I'd have a sub 2 over a sub 1. So that gives me a ratio of negative 5. Let's check the next one just to be safe. If I take 50 over negative 10, I also get a ratio of negative 5. Okay, so the common ratio for our first series is going to be negative 5. Let's take a look at this next one. I have r is negative 24 divided by negative 48. That's going to give me positive, because 2 negatives make a positive 1/2. Okay, let's try that again. If I take negative 12 divided by negative 24, I get positive 1/2. So what we're doing each time is we're multiplying by a half. So this sequence could be defined as a sub 1 equals negative 48, and then a sub n would equal a sub n minus 1, right? This is our recursive definition. Times 1/2. Same thing for example 1 up here, right? Our recursive definition, just so we get some more practice in, would be if a sub 1 is 2, then a sub n equals a sub n minus 1 times negative 5. So in a geometric sequence series with the first term a sub 1 and the ratio r, the nth term is always given by the following, okay? A sub n equals a sub 1 r to the n minus 1, right? Because we're just multiplying by a constant. So if I had a sub 3, that'd be if I had a sub 2, that'd be a sub 1 times r to the first, right? Well, this is a sub 2, so if I have a sub 3, that'd be a sub 1 times r to the second. So, if a sub 1 is 4 and r equals negative 3, I want to find a sub 6. So a sub n equals a sub 1 r to the n minus 1. I have a sub 6 equals 4 times negative 3 to the 6 minus 1. So a sub 6 equals 4 times negative 243, which is negative 3 to the 5th. So I get that a sub 6 is negative 972. Now, given a sub 1, a sub 2, and a sub 3, I want to find a sub 7. So So I know my a sub 1 is 3/4. What I don't know is my r. So I need to figure out my r. R is a sub n plus 1 over a sub n. So I'm going to take 3/8 divided by 3/4. That equals 3/8, right, divided by 3/4. In order to divide fractions, we keep the first fraction the same, change from multiplication to division, and flip the second fraction. You can see my 3's are going to cancel. I get 4/8, which is 1/2. So that's going to be my r. So now I have a sub n equals 3/4 times 1/2 to the n minus 1. So a sub 7 equals 3/4 times 1/2 to the 7 minus 1. A sub 7 is 3/4 times 1/2 to the 6th. This is going to give me 3/4 times 1 over 64, because 2 to the 6th is 64. So I get 390 seconds. Now remember, in order to multiply fractions, I multiply the numerators and I multiply the denominators. So that's how I solved that question. So if a geometric sequence has the first term a sub 1 and the common ratio r, then the sum of the first in terms is given by the following. S sub n equals a sub 1 over 1 minus r to the n, where r doesn't equal 1. Now let's think about what that would mean if r was 1, right? If r was 1 and I had a sub 1 equals 2, well then a sub 2 would also equal 2, right? Because each time we're multiplying by r, which is 1, right? This is a sub 1 times 1, which is 2 times 1, which is 2. And then I'd have a sub 3, which is a sub 1 times 1 squared, which is still going to be 2 times 1, which is 2. So that'd be really boring. So we don't want that. So let's go ahead and work through an example using this equation. So I have, if a is 1, a sub 1 equals 4, and r equals negative 3, I want to find s sub 6. So let's remind ourselves that s sub n equals a sub 1 times 1 minus r to the n over 1 minus r. So I have s sub 6. So now we're looking for the sum of the first 6 terms, equals 4 times 1 minus r, which is negative 3, to the 6th over 1 minus negative 3. So I have s sub 6 equals 4 times 1 minus negative 3 to the 6th is actually 729, over 1 minus a negative 3, which is 4. These two 4's are going to cancel. So I get 1 minus 729. So I'm going to get a negative 728. So that's going to be the sum of the first 6 terms. Next, given 3/4, 3/8, and 3/6, we want to find s sub 4. In a couple slides back, I figured out that the common ratio for this function was 1/2. If you're not quite sure how I did that, you can take 3/8 divided by 3/4 or 3/16 divided by 3/8 to find r. So I'm going to have s sub 4 equals 3/4, that's my a sub 1, right, times 1 minus 1/2 to the 4th over 1 minus r, which is 1/2. So I get 3/4 over 1/2 times 1 minus 1/16. That gives me 3/4 times 15/16. That gives me, over 1/2, that gives me 45/64 divided by 1/2. 45 over 64 divided by 1/2 is the same as 45 over 64 times 2 over 1. That gives me 90 over 64, which we could simplify to 45 30 seconds. So this is the sum of the first 4 terms of this sequence. Now, it's important to note that the sum of a sequence is called a series, okay? We're going to denote this with the Greek letter sigma. This is actually a capital sigma. So if I have a finite series that goes from the I to n, right? Remember n being related to the natural numbers. It's just the sum of all the terms, all the a sub I. We use I as an index. We call this the index of summation. For an infinite series, we would denote this as I equals 1, because, right, that's where the natural numbers start. Oops. All the way to sigma. So we're just trying to find a sum. So when we are given a series, we need to determine if it's geometric or arithmetic and go ahead and find the sum using this S sub n equations we've used previously. Okay? So let's take a look at a couple examples. I want to find S sub n I want to find the sum for the first 13 terms of this. Now this is 6 times I minus 2, okay? So not only are we taking away something, there's a difference, but we're also multiplying. So what we're going to have to do is we're actually going to have to find all of the terms of this sequence. Nope, I'm mistaken. Okay, so we're going to be able to use the S sub n equation. So S sub n equals n over 2 times a1 plus an. Well, a1 is going to be when I equals 1. So I'm going to have 13 halves times 6 times 1 minus 2. And I'm going to go ahead and add that to 6 times n, which in this case is 13 minus 2. Okay? This gives me 13 over 2 times 10 plus 76. That gives me 13 over 2 times 86. So I have 559. We're going to do the same thing for this second equation. My neighbor decided it was the perfect time to mow. Great. So for this second equation, let's go ahead and use the same formula. So I have S sub n, so in this case it's 5, we're looking for the sum of the first 5 terms, equals 5 halves, so 5 over 2, times a sub 1, which is 5 plus 3 times 1, plus a sub n, which is 5 plus 3 times 5. Don't forget our PEMDAS. I know this looks like a lot of parentheses, but we need them. I'm sorry. So if I have S sub 5 equals 5 over 2, that leaves me with 5 times 3 plus 1, which is 5 plus 3 times 1, which is 8. And then I have 5 plus 3 times 5, which is 20. So I have S sub 5 equals 5 halves times 28, which is going to give me 70. So the sum of this series is 70. Let's take a look at these. At these functions, we have an R, right? These are geometric. We aren't adding or subtracting anything. We're multiplying. We've got I as an index. So let's go ahead and find the first couple terms so that we can determine the ratio, right? We want to find R. So a sub 1 in this case would be 3 times 2 to the 1, which is 6. A sub 2 in this case would be 3 times 2 to the second, which is 4. So 3 times 4 is 12. A sub 3 would be 3 times 2 to the squared, which is 8. 3 times 8 is 24, right? So if I wanted to find my common ratio R, it would be 12 divided by 6, which is 2. And we also see that 24 divided by 12 is 2. So this is our R. So then I can use the summation equation for geometric series. I have S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. This gives me S sub 6, which is equal to a sub 1, which I found, 6, times 1 minus 2 to the 6, over 1 minus r, which is 2. So I have s sub 6 equals 6 times 1 minus 64 over negative 1. That gives me negative 378 over negative 1. So my sum of my first 6 terms is a positive 378. All right, now for this second example, it's important to note that here I have 1/2 to the I, right? This is the way we're going to make this geometric. So each time we're multiplying by 1/2. Okay, so a sub 1 would be 1/2 to the first power, which is 1/2. A sub 2 would be 1/2 to the second power, which is 1/4. And a sub 3 would be 1/2 to the third power, which is 1/8. And then we would find our r to be 1/2. So I have that s sub in this case 4. Let me go ahead and change this pen color. Let's go with green. I have s sub 4 equals a sub 1, which I found to be 1/2, times 1 minus r, which is 1/2, to the n, which is 4, over 1 minus 1/2, which is just a half. So I have 1/2 times 1 minus 164 over a half. Well, these 2 1/2s are going to cancel. So 1 minus 1/64 is going to be 63/64. So the sum of the first 4 terms of this sequence is going to be 63/64. Now, it's important to note that if the terms of a sequence get closer and closer to some real number, the sequence is said to be convergent and converge to that real number. So for example, a sub n, if it's equal to 1 over n, approaches 0 as n increases, right? If n equals 1, a sub 1 is 1 over 1, so 1. If n equals 2, a sub 2 is 1/2. A sub 5 is 1/5. Can you see we're getting closer and closer to 0? I could have a sub 1,000. That'd be 1 over 1,000, right? Because the natural numbers are infinite. They go on forever. I could have a sub 1,000,000. I forgot a 0 there. That would give me 1 over 1,000,000, right? And that's getting really, really close to 0. So we would say a sub n converges to 0. So the sum of a geometric sequence where r is less than 1, right, that's a fraction, so the sum's going to be converged, can be found because s sub infinity equals a sub 1 over 1 minus r. So let's go ahead and go through this example. So in this case, I have s sub infinity equals a sub 1, well, 2 to the 5th to the first power would just be 2/5. So a sub 1 over 1 minus r, which is 2/5. That gives me 2/5 divided by 3/5. So I'm going to take 2/5 divided by 3/5. I remember to keep change flip. I keep my first fraction the same. I change from division to multiplication, and I flip my second fraction. These 2 5s are going to cancel, so I'm left with 2/3. So I would say this infinite geometric sequence converges to 2/3. Okay, it's important to note that our r value has to be a fraction. A fraction is what's going to make our sum converge. So let's go ahead and work on another example. I have negative 2/3 times negative 1 over 4 times I to the minus 1, okay? So I'm going to go ahead and find my a sub 1. A sub 1 is going to be negative 2/3 times negative 1/4 to the 1 minus 1. Well, 1 minus 1 is 0. Negative 2/3 times negative 1/4 to the 0. Any number to the 0 is going to, 0 power is going to be 1. So I have negative 2/3 times 1, which is just negative 2/3. Okay? My r in this case, what's going to be changing by is it's going to be changing by 1/4 every time. So r equals negative 1/4. So the sum of this infinite series is going to be my a sub 1, which is negative 2/3, over 1 minus negative 1/4. So I have negative 2/3 over 1 plus 1/4. So I have negative 2/3 over 5/4. So negative 2/3 divided by 5/4. That's negative 2/3 times 4/5, right? We keep, change, flip. That gives me negative 8 over 15. I can't simplify that any further. So this infinite series converges to negative 8 over 15. So, for example, a sequence of any numbers that does not converge is called divergent. Let's take a look at this. A sub n equals n squared. So if I have a sub 1, 1 squared is 1. A sub 2, 2 squared is 4. A sub 10 would be 10 squared, which is 100. A sub 100 would be 1,000, right? Our number keeps getting bigger and bigger and bigger. It doesn't converge to anything. It doesn't have a common ratio. So we would say this is divergent. So are the following convergent or divergent? Okay, so I need to figure out what they approach. It's not necessarily if they have a common ratio, it's whether they approach something. Okay, so in this case, I have a sub n is n plus 1 over n plus 2. So a sub 1 would be 1 plus 1, so 2 over 3. A sub 2 is 3 over 4, because I take 2 plus 1 to get 3, and 2 plus 2 to get 4. A sub 3 equals 4/5. A sub 10 would equal 11/12. A sub 100 would be 101 over 102. I hope you can see that these values are getting closer and closer to 0, right? This was like 0.6, 0.75, 0.8 if we converted these to decimals, right? This is like 0.8 something, this is like 0.9 something, right? We're getting closer and closer. So this converges to 1. It gets closer and closer to 1. Let's take a look at this. I have a sub 1 equals negative 1 to the first times 1, which gives me negative 1. A sub 2 equals negative 1 squared times 2, which is 2. A sub 3 equals negative 1 cubed times 3, which is negative 3. What we're going to see in this series, if I write out the first few terms, we're going to have negative 1, 2, negative 3, 4, negative 5, 6. And what you can see is we're bouncing back between negative and positive. And because of this, our sequence is not going to converge. So this example is divergent. All right, last but not least, I have a sub n equals 2n plus 1, okay? So I get n squared plus 2. So here I have, if n is 1, I have 2 times 1 plus 1 over 1 squared plus 2, so I get 3 over 3, which is 1. Okay, cool. I have a sub 2, that would give me 2 times 2 plus 1 over 2 squared plus 2. So that gives me 5 6. A sub 3 is going to be 7/11, right? And as we can see, my numbers are starting to get smaller and smaller. I had 1, now I have 5 6, now I have 7/11. If I had a sub 10, that would be 21/102, right? If I have a sub 1,000, a sub 100, that would give me 201 over 1,002, right? So this is kind of like 0.2, 0.2, right, if I have a sub 20,000, sorry, a sub 10,000, that would give me 20,000 over 100,000 and 2, right? So I'm kind of getting closer and closer to 1/5. So this converges. So let's take a look at an example. If I have a ball and it's dropped from a certain height, it will rebound 3/5 of the original height. So how high will the ball rebound after the fourth bounce if it was dropped from a height of 10 feet? So I know that my first drop is 10 feet, right? I'm going to call it a sub 0. After my first bounce, right, I have a sub 3/5 times our 10 feet. That gives me 6, right? So this is after our first bounce. So I want to know what it's going to be after our second bounce. Okay, so I'm going to take a sub 2. This is our bounce 2. That gives me 3/5 times 6, which gives me 3.6. For my second bounce, I'm going to get 2.16. And for my fourth bounce, I'm going to get 1.3. That doesn't look like a 3. I should probably fix that. Oops. So, how high will the ball rebound at the fourth bounce if it was dropped from a height of 10 feet? It's going to be 1.3 feet. Last but certainly not least, in a certain community, the consumption of electricity has increased by 6% each year. Okay? If a community uses 1.1 billions of electricity right now, how much will it use 5 years from now? So this year we've got 1.1 billion. And as long as I remember that my units are billions, I can not write out all those zeros. So on my equation, my function's a sub n equals 1.06 times a sub n minus 1. Okay? I have a sub 1 is 1.06, right? That's 100 0.06, a 6% increase, 0.06, times 1.1 billion, and that would give me 1.166, okay? Now this is going to be a sub 2, which is 1.06 times 1.1, which gives me 1.23596. A sub 3 equals 1.31. A sub 4, we'd find 1.38. And a sub 5 would be 1.47. Okay? Now what I want us to see, though, is that for a sub 2, and the same thing's true for the previous problem, a sub 2 equals 1.06 times 1.116, which is 1.06 times 1.1, right? This is 1.06 squared times 1.1. So this would allow us to write this as a geometric series. I have a sub n equals 1.06 to the n times our original amount of 1.1. This would be a nice, better way, especially what if they said how much to use 50 years from now. Using a geometric sequence would allow us to calculate this more easily.